you open an account with a bank and you do transactions. I want to add money to my account, I want to withdraw some money from my account, and maybe I want to do some transfers with someone else in another account, so the bank has some protocol to ensure that this money can flow from one bank to another. Okay, so if we look at the big picture from database and distributed computing perspective, we usually use this picture of a check. Okay, what are the fields in a check? So we can say we have what we call identities and signatures. So what's an identity? Identity is like myself. I'm writing a check. So the check here says that this comes from me, and I'm going to sign here to say, so this is my check, and I'm signing here to ensure that this is me, right? And then you can think of that also, your signature is your password, and your identity is your username. So if you have an account, so like your username is your identity, and your signature is the password, okay? And there is a ledger, okay? So a ledger is simply a database. We want to keep a record of how much money is owned by every identity, and this is saved in a database. And then we have transactions, which basically does move money from one identity to another. I want to give you some money, so I sign a check that belongs to me, and say give it to someone else, right? And then we have the problem is that someone would try to spend or give a check to two people to spend the same money twice. So we need to prevent that. So in database context, what we do is we use what we call concurrency control protocols to serialize transactions, to make sure that transactions on your account are happening one after the other after the other. So if you try to spend your money twice, what's going to happen is the first one will succeed and the second one will fail. So that's what concurrency control is for. And that's for to prevent double spending. By the way, if you have any question at any moment, just feel free to raise your hand and interrupt me. I would like a conversation, so it's not a one-man show. Typically, in our language, we use what we call a log, and the log, we write the transactions, what we did, and that's like a bag for a database to make sure that these are the transactions that happened, and we put them in some order. And the log, we assume, we trust that the log is persistent. And also we assume that it's immutable and tamper-free. Why we do that? Because we trust the banks. So we trust that no one can go and change the log of transaction. We have this much trust in the banks. But if the bank got hacked, and someone hacked the copies of our data, they can change that, and definitely the log can be tampered with. So why do we assume that the log is tamper-free? Because we trust the banks, that's all. And definitely the bank employs so many security engineers and all these people to ensure that this should happen, but we have heard of so many banks and organizations that has been hacked, so I mean, this trust may be not in the right position. So this picture gives us how our data is represented in the bank and what type of trust that we put in the bank. So we assume that our data is in some database that is backed by a log, and we assume that the bank is replicating our data in many locations, such that if some location fails, we can still do transactions on our data. And we assume also that all these copies are secure, no one can have access or play with them. And we also assume that anyone who is communicating with the bank, that the connections are secure. So these are all assumptions. They're built on technology, but there are also lots of trust on that. Okay, so what does Bitcoin? So why I'm talking about Bitcoin? So first of all, Bitcoin, or the paper by Satoshi Nakamoto, was the first one to introduce the concept of blockchain. But this talk is talking more about blockchain. We are mentioning Bitcoin many, many times because it was the first paper, but this can be applied to any other paper that's using blockchain, and in more sense, what we call open blockchains. I'm going to talk about that later. So the whole idea here is that instead of depending on the bank to do transactions, what we want is to replace the bank with a network of nodes that maintain our data. Okay? And this network of nodes are running computers, and they have a copy of the data. So by doing that, what we want to to ensure is that there is no single node that we trust. Our data is replicated in many, many nodes, okay? And this replication is done in a way, which is the blockchain idea, that it's really hard to tamper it, to change anything on it. So I'm going to talk about that. So the whole idea is that we want to replace a centralized bank with a decentralized network of nodes. Okay, so back to the same concept that we talked about in the banking. So the first paper was published by Satoshi Nakamoto, which some person or a group, we don't know, but the title was Bitcoin, a peer-to-peer electronic cash system. And from our perspectives in databases is that we're going to use also identities and signatures, but instead of using what we call username and password, we're going to use what we call cryptographic methods, public and private key. So the way we think about it is that the public key is my identity and the private key is my signature. So the public key is something, so a metaphoric example, public key is like your email address. You give it to everyone. Private key is your password. So you are the only person who can read emails for this email address. But anyone else can use your email address to send you an email. Okay? So that's the public key and private key. And then the ledger, so it has the balance of each identity, and we save that in the blockchain. We're going into the details of that later. And then we have transactions. So what are the transactions it says? We want to move some bitcoins from one identity to another. So I have some bitcoins. I move it to Muhammad at the back. And we must have some concurrency control protocols. Remember, we use concurrency control to prevent what we call double spending. So we need the same here. We're going to do that through what we call mining or proof of work. We're going to explain that in details later. And the same assumption that the transactions are backed by a log. So the log in this case is the blockchain, and it's persistent because it's replicated across the network node. So if one copy failed, it's still, there are so many copies. And it's immutable and tamper-free, but it's not based on trust, it's based on code. So it's based on proof of work and hash pointers.
Proof of what?
Of work.
Work?
Yeah.
W-O-R-K?
Proof of work, W-O-R-K, yeah.
Okay.
Yeah. And hash pointers. So I'm going to talk about this in details. Okay. Some computer science background that we're going to use throughout the talk. Digital signatures. What is a digital signature? So a digital signature, as we said, we have the public key and the secret key, or the private key. Think of this as your email address, and this is as your password. And there is some function that generates a pair for you, public key and secret key. So how we can use it? So your public key is your identity, and the secret key is your signature, and public key is made public and used to verify documents that are signed by you. What does that mean? So now we have two parts. A public part, everyone can see it. A private part is only kept at my side. Okay, so how does it work? So there's some function named sign that if I give it a document and my secret key, I will run it on my machine, it will generate what we call a signature. It's similar, pretty much similar to you signing a check. Okay? The only difference, to verify that this is your signature, if I have the document, the original document, and your public key, and the signature that was generated from this function, I can verify that you actually signed this document and no other document. Okay, let's make this a little bit clearer. What's the difference between a digital signature and a physical signature? So a physical signature, I can take a picture of it and put it in another paper, right? And still it's the person's signature. A digital signature doesn't work this way. A digital signature is unique for every document, which means if you try to take my signature and put it in another document, it wouldn't work. I can verify that this is, you're trying to fraud or do something bad. Okay? So, what are we going to do? We can verify only using the signature and your public key, which is made public to everyone, and the document that you actually, this signature was signing the document with the secret key. So far, so good? This is important. If you have questions here, please stop me. Okay? That's what the digital signature is doing. Notice that we're using these digital signatures for authentication, not for privacy. We're not doing encryption. The document is public for everyone. Okay? My public key is public for everyone. The only thing that's secret is my secret key. And what are we trying to do using the verify function is to verify that this secret key was used on this document to generate this signature. And we are doing it without revealing the secret key. Okay? Okay? So how are we going to use this? So digital signatures, it's unique to the signed document. It's very hard to forge, and it's very easy to verify. Yes?
I'm thinking in terms of like if you sign an actual check, you have to have
Right.
something to reference it to know that that signature is the person's. How can it reference to verify without knowing what the signature is?
So you can confirm or verify that this secret key is used to sign this document through this public key.
Okay.
Okay? So the public key is saying that this person signed this document. And me, myself, I will publish my public key everywhere. How would you ensure that it's not someone else is trying to impersonate me? So that's another story. But if you have my public key, and you have a signature that's coming from me, you can ensure that I signed this using my secret key. Okay? So the link to the person is through the public key. The link to the document is through the document itself, and the signature just says that this secret key signed this document. Okay? Now, how are we going to use it? So digital signatures and Bitcoin. So you can think of a Bitcoin. The difference between a Bitcoin and a dollar banknote is that in a dollar banknote, if I give it to you and then you give it to someone else, no one can trace it back to me, right? It's just a piece of paper that's moving around. We don't know where it came from. We don't know where is it going. But for a Bitcoin, you can think of a Bitcoin as a sequence of digital signatures. What does it mean? So coin owner digitally signs their coin to transfer them to the recipient of the coin. Okay? So let's say Alice wants to move a Bitcoin to Bob. So I'll take my Bitcoin. Let's refer to my Bitcoin with this icon. I'll take the public key of Bob. So Bob announces their public key. And the goal of this operation is to transfer my Bitcoin to Bob. Okay? I'm going to put these together, and I'm going to sign them using my secret key. Okay? Yes?
So, from the previous slide, the Bitcoin is like the document.
Right.
Slide.
Actually, you can think of this as these two together is like the document. Okay? So the Bitcoin and the destination, the person who is receiving this coin, is the document. Okay? That's a very good question. And I'm signing it with my signature. So I generate a signature that says, I'm moving this Bitcoin from Alice to Bob. Anyone who has access to the document, which is the Bitcoin, and Bob's public key, and access to my public key, which is the public key of Alice, and the signature that was generated, can verify that Alice herself is the one who signed this transaction, and no one else. This is an important point. So is it clear? Yeah? Okay, so can we verify that and say that this is a valid? Okay, so what if Bob wants to move his coin to Diana? What I was going to do is, now think of this coin. Showed you a picture, but what is this coin actually? It's this signature. So what says that this coin is owned by Bob now is that Bob has a signature that says that this coin came from Alice. Okay? So the ownership of Bob for this coin is just proven by having this signature. So this signature is the coin itself. Yes?
So just a clarification question. So in order for the transaction to be complete, it requires a sort of a third-party verification. What was the reason?
So we haven't talked about that yet. I'm just saying what should be done to move a Bitcoin from one person to another. So I have a signature that moved this coin to me from someone. So as Bob in this case, I got this signature from Alice, right? Now I want to move it to someone else, I have to sign it someone else. So think about this Bitcoin, the pictures that I showed you, as a signature that came to me from someone else, and I am paying it to someone else. Okay? So Alice got it from Alex, and Alice is moving it to Bob, and Bob is moving it to Diane. Okay? Yes?
Sorry, so the Bitcoin itself is just the set of all signatures
Yes.
in creation?
Yes.
Okay,
So think of a Bitcoin as a sequence of digital signatures.
okay.
Okay? So now I want to move it to Diane. What I'm going to do the same thing. Put the public key of Diane, compress it with the signatures that moved this Bitcoin to myself, and then sign it as Bob. Okay? So I generate these signatures that says, now this coin is owned by, from Bob to Diane, is owned by Diane. Okay? And anyone can verify that. So a big picture of a Bitcoin is, Alice got this coin from someone. So Alice wants to transfer it to Bob. I put the public key, combine it, and sign it with my secret key. Generate a signature from Alice to Bob, so now this coin is owned by Bob. Bob wants to move it to Diane, does the same thing, and sign it with their secret key. Generating a signature from Bob to Diane. And so on and so forth. Yes?
Okay, so you're saying that Alice got this from Bitcoin from somebody else.
Yes.
Ultimately, there's somebody who didn't get it from somebody else.
Correct. That's a very good question. So we're going to address this point
Oh.
very soon. But this is a very good question. So that's what we are asking in this slide. So far, we didn't say anything about how would we combine the previous signature and the public key. We didn't say anything about double spending, and we didn't say about what does the first signature look like. That's your question, right? Yeah. Very good question. We're going to talk about that while we are explaining the detail. But so far, so good? Okay, let's take them one by one. What's the combination function? How would I combine these two, the signature and the public key of the destination? So the technique that we use in computer science, we call it hashing. It's basically a function that takes some document and generates a fixed size output. And think about it as a way of compression. But the thing about hashing is that if you give it any document, it will generate the hash for you. But if you give it a hash, it's really, really hard to get the original document from the hash. So it's somehow one-way function. I'm giving it some document saying, hash this document for me. It's very easy, it will generate this hash for you. But if you give it a hash and ask it what is the original document, it's very hard to revert it back. Okay? So signature and public key are combined using hashing. A hashing is a function that takes a string of any length and output a fixed size output. So for example, 256 bits. So it's very efficient to compute, and it satisfies the following properties. One, it's collision free. So there is an assumption that for any two strings, x and y, the hash of x if the hash of x and the hash of y are equal, then x and y must be equal. You can find two strings where the hash of them are equal. Of course, this is not really true, but with very low probability collision can happen. Anyway, the other thing is that if I have the hash of x, it's really hard to find x to revert the hash to the document. But if I have the document, I can find its hash. And then let's skip this for now. So Bitcoin uses a hash function named SHA-256. So think about it that we SHA-256 the previous signature and the public key of the destination, and we get a unique string of 256 bits. To give you an example, this is the output of SHA-256 as the string ABC, and this is the output of AB capital C. It's completely different. Okay? So that's how we combine the public key and the signature. Now, what about double spending? So double spending, it's basically you're trying to spend the same digital asset more than once. Yes?
So you described hashing,
Yes.
But then you also described signing with a signature, with your secret key.
Yes.
So, you haven't talked about how these two are related to each other.
So you sign with your secret key the hash document, right?
Also, it's hashed first, then
sign.
Okay.
Yeah. But anyone can verify that the previous signature was combined with the public key of the destination through this hash function and then signed with my secret key.
Okay.
So how would I know that you own this coin? Is that basically I can verify that the signature has you as a destination before it was generated. That make sense?
Yeah.
Okay. So double spending. What is the problem here is that someone is trying to spend the same digital asset twice. And it's impossible to do in physical cash. I mean, I can't take the dollar and give it to someone and give the same dollar to someone else. You don't do that. Actually, cash is amazing. Anyway. It's usually prevented in traditional banking through concurrency control. So, if you try to do a transfer from your bank account to two people with the same amount, with the same money, it will be prevented by the concurrency control algorithm in the bank. All right, so let's have a look over double spending in case of Bitcoin. So far, we talked only about signatures, right? So if I'm Alice, I can sign my document to Bob. Sorry. I can sign my coin to Bob. Sorry, if I am Bob, I can sign my coin to Diane, and I can sign it to Marty. And try to convince both of them that I am Bob, and I actually did, this is a valid signature, and this is also another valid signature, right? So I try to say, okay, hey, this is my Bitcoin. I sign it once and give it to Diane, and I took her card. And I sign it another time, and I give it to Marty, and I took his ring, right? That's silly. That has to be prevented. So how would that happen? One way you can do that is to depend on a third party, also a third party, just to make sure that you haven't signed this coin before to someone else. But so how it goes? I have 50 Bitcoins. I want to move 20 of them to Diane. How would I do that? I go to Trent, the third party, and say, hey, I have these 50 Bitcoins. I want to give 20 of them to Diane. How would Trent do that? So Trent would check in his records, oh, this signature wasn't spent before, so I'm going to shred it and generate two signatures from Trent to Bob and from Trent to Diane. Diane has 20 Bitcoins, and now Bob has 30 Bitcoins. Well, that's super silly because basically Trent is the bank. Okay, it's the same idea. So we haven't done anything new. So how is that done in the Bitcoin domain? So we want a decentralized solution. So how does that happen? How does that happen? So basically, the Bitcoin network, which is the nodes that maintain the ledger, so it's a network of nodes that maintain the ledger. Okay? And they work to agree on some transaction order. So basically, as we said before, double spending could be prevented if we have some order for transactions. So basically, if I'm trying to spend the money to two people at the same time, if this transaction happens first, so the second one will be rejected. If the second one happens first, the first one will be rejected. If we have a total order of the transactions, double spending can be prevented. So what we want to do is serialize transactions on every coin to prevent double spending. So the question now is, what is the ledger? How does it look like? How would the nodes agree on the transaction order? Okay? And what is the incentive for this network node to maintain the ledger? Why are they running their computers to maintain the ledger? Okay? These are all questions that we keep asking. So what's the ledger? It's a blockchain, finally. Talking about blockchain. So, yay. So what's the blockchain? Basically, it's a chain of blocks. Transactions are grouped into blocks. And the blocks are chained to each other through what we call pointers or something. And hence we name it blockchain. It's a chain of blocks. Okay, so we can look at it this way, that we have a block, has a bunch of transactions, and then another block that has some other group of transactions. I mean, I'm giving them the same indices, assuming that at most n transaction can be in each block, but these are different than those. And then there is a pointer to the previous block, okay? So a block chained to the previous blocks, and so on and so forth. So that's what blockchain is, but what are the details? So where is the ledger stored? So basically each network node maintains a copy of the ledger, okay? So this chain of blocks is replicated in every network node. Then how is the ledger tamper-free? How would we ensure that none of the network node can go and change this transaction, right? I want to make sure that no one can change the transactions and convince everybody else that this is the right version of the blockchain. So blocks are connected through what we call hash pointers. Again, using hashing. So what hashing is doing is to say that in this block, I'm going to store a field that has the hash of the previous block. Okay? Remember from hashing, if you change anything in the input, the output of the hashing is completely different, right? So if anyone tamper the content of this transaction, the hashing here will not match. So we can easily detect if someone changed anything in any of the blocks. Why is that? Because the hash of this block is stored here. The hash of this block is stored in the next block, and so on and so forth. Okay? So if anyone tries to change the content here, the hash will not match, so we'll detect that there is a change here.
But it's not the whole hash.
It's the hash of the previous block.
The entire thing, all 32.
What do you mean all 32?
I thought it was 32. There's a whole bunch of numbers, right?
Right. It's the
And
hash
it's
of.
not all of those that transfer. It's only a certain
So
number of them.
think about this as one document. We pass this document to the hash function. It generates a 32-byte string. Okay, so it's a compressed version of the block. So if anyone change anything in this block, the hash will not match. Yes.
So basically, is the idea is that every hash pointer is a checkpoint.
Right.
Check whether it's.
It's check of the previous block to ensure that no one changed anything in the previous block. Did I answer your question?
So the whole hash of the previous one goes into the next one.
Right. So this is 32 bytes.
And then the 32 bytes, so it now becomes 64 bytes?
No. So basically, you hash this block, it gives you 32 bytes here, right? So we have 32 bytes that represent this block in the next block. Now, if you hash the whole document here, it will generate 32. That will come in the next, will go in the next block, and so on and so forth.
So the next one,
The hash here is the hash of the block, right? Of this block. This block has the hash of the previous block. So the hash function is hashing the whole thing, including the hash of the previous block. That makes sense? But the output is of a fixed size anyway. It's 32 bytes. Yes?
So on the actual, like when you record it, is it just one, is it a different number for every single block, or does every single transaction show up?
So you have a block that has transaction 1
Okay,
till
so
transaction n.
Right.
Then you hash the whole thing and store this hash in the next block. So this is the hash of 1. Okay? And there are other transactions here. So name it n plus 1, n plus 2, and so on and so forth.
So going in reverse order, would you get that header hash? And how would you like go in the reverse order to actually double check that it's the same transaction?
So you basically have a copy of all the blocks, right? You want to make sure that no one tampered anything here, right?
Right.
So you can basically hash this and check in the next block. We store this in, if you have a copy, you store them in blocks one after the other, but you want to make sure that no one tampered anything in one block.
Yeah.
Okay?
Yeah.
So the way we hash it stays the same.
Yeah, so we think about this as SHA-256. Yeah? And then you hash the whole thing here and put this hash in the third block. So this is hash of 2. Okay? And you have a bunch of other transactions. Okay? So far so good? Yes.
So, what is SHA-256?
It's a hash function.
That's just a random, okay, so
Just an example.
every time it's changing.
So it generates a 32-byte unique string for every input. Yes.
For any input, so
For any
it
input.
can be any length, it can be one letter or it can be a whole set of transactions.
Right.
It always returns 32
Bytes. So it returns 32 bytes if you give it any string. But for every string, for every unique string, the output is unique. Yes.
Is there a limit to transactions in which a block can?
Yeah, so we're going to talk about that, but let's assume that there are n transactions per block. Yes. There is a limit.
I just wanted to know what N was for Bitcoin.
So for Bitcoin, a transaction, the block is 1 megabyte.
Okay.
So you just need to know how big is a transaction, and then divide a 1 megabyte over the number of bytes per transaction. Okay? It was, I think, at most around 4,000 or something.
So,
I can't remember exactly the number, but when you sum it up, it will be 7 per second at most.
okay. So if you, the ledger keeps growing in size,
Right.
right? So it must already be, is it what's it now, like gigabytes, terabytes?
Yeah, it is in range of gigabytes.
So it's going to keep growing.
200 gigabytes may probably
Because
for.
the entire history of all transactions since the currency was started is stored in the ledger.
Right, correct. And there are some details about how to garbage collect some blocks, but we're not going to cover this in this talk.
Okay.
Yeah, but yeah, there are techniques on how to garbage collect and have a compressed version of the previous history.
So can I just find the ledger and download it to my?
Yes, you can do that.
So I have another question,
Sure,
which might be going off on a tangent. If it is, you can just tell me.
sure.
So you said this is done in order to discourage tampering of any one of these hash blocks.
Correct.
I thought another thing that discouraged the tampering was that each one of these hash blocks is replicated on many different computers. So
Correct.
it would be difficult to go in and tamper with all of them when it's not even known how many there are.
Right. So that's a very good point, and that's the second component of the tamper-free. So tamper-free, yeah. So I'm going to talk about that in a moment. So each block contains the hash of the previous block. The hash gives the block its location in the blockchain. So basically, block 2 has the hash of block 1, block 3 has the hash of block 2, and so on and so forth. And then tampering the content of any block can easily be detected. But the question now is this enough? That was your question. No, it's not. So if I tamper some transactions here, the hash wouldn't match, and that will be inconsistent, right? It can be easily detected. But then if someone would say, hey, I'm going to change the whole chain. Change these two transactions and change the hash, and the next block I'm going to change the hash here, change the whole, everything. And this is now consistent. Like if you go to the third block, you'll find that the hash here matches the hash of the current block. So this is now, is this possible? So that action should be prevented. So the hashing is not just enough. You have to do something more. And that also goes back to the replication aspect we talked about. So far, as we said, we can replace a consistent blockchain with another tampered consistent blockchain. But this action should be made very hard. So how are we going to do that? So let's take the big picture. We have nodes who are maintaining the chain. We're using different circle size to refer to different computing power. So each node, the bigger the node, the more computing power it has. And then each has its own copy of the blockchain, right? And what we want to do is that some of them, we need to make progress, right? So to make progress, we need to agree on what's the next block. And then we all agree that this is the next block, so we move forward and try to agree on the following blocks, and so on and so forth. So the ledger is fully replicated for all the nodes. To make progress, the network nodes group new transaction into a block, and blocks are fixed size, it's 1 megabyte. And network nodes need to validate the transaction to make sure that they don't conflict with each other or they don't conflict with the past. What do we mean by conflict? Is that none of these new transactions is trying to double spend money that was already spent or trying to spend some money twice in the same block. Okay, that's briefly what a conflict is. And network nodes need to agree on the next block to be added to the blockchain, and that's how we make progress. So we call this problem consensus. And this problem has been studied so many times in the distributed systems context and database, and there are many solutions for the consensus problem. But what are the limitations for them? So the previous solutions, I don't want to go over all the details of the next couple of slides, but the idea of consensus is that the network nodes need to agree on the next block. How are we going to do that? So we can use traditional consensus algorithm. What is different between what Nakamoto proposed in his paper and the traditional algorithm is that in the traditional algorithms, we assume that we know all the people who want to agree. Okay? Like I am a company that has 3 replicas of the data, and I want this 3 replica to agree on the order of transactions. So I know that there are 3 replicas. I know where they are. While here, the network nodes are, it's an open network. Any node can join. You can run a node in your laptop, right? It wouldn't be efficient, but you can theoretically do that, right? So now, how would we do consensus between a group of nodes that we don't know where they are, how many of them, and what are their identities? That's the big question that Nakamoto is trying to answer. So in the next slides, I think I'm not going to go over the details here, but the problem of consensus has been studied a lot in the literature, but through just assuming that we know who are the nodes that wants to agree. Okay? Just forget about that, and let's talk about this idea, the Nakamoto consensus. How would we reach consensus? How would we agree on the next block in the blockchain through what we call mining? So intuitively, we have so many nodes, right? We don't know how many of them. Each of them is trying to propose the next block, right? So how would we limit the number of people who can successfully propose the next block? We ask the network node to solve a puzzle, okay? And this puzzle is super hard. It takes a lot of computational power to solve this puzzle. But whoever solves this puzzle gets the right to introduce a new block to the blockchain. Okay?
It also gets a bunch of money for doing so.
Right. So that's the incentive to solve this problem, right? So the puzzle is computationally expensive. Once a network node finds or mines a solution, it adds a block of transaction to the blockchain, and it sends this block to everyone else. And once other nodes receive this solution, they accept and verify the solution. Yes?
So is it the case that it's computationally trivial to verify the solution?
Right. It is
Like
computationally trivial, like hashing.
Okay.
Yeah, it is computationally trivial to verify the solution.
A question?
Yes?
So when it multicasts, does that mean everyone has to be online and they have active internet connection?
Not true. You send, it's best effort. You send to whoever you can reach. And everyone just multicast the solution to everyone, and that's it. So to answer your question, there may be some nodes who are trying to add a previous block that is already added, because they haven't heard about it. Okay? So they don't have to be all on the same page. But what's going to happen is that over time, eventually you will hear about these blocks, so you're not going to keep searching for them. Okay? All right, so the mining details. I have a mining node. I have a copy of the blockchain. Users keep sending me transactions. I verify them. Okay? And the part of the verification or the validation process to make sure that none of these transactions is trying to double spend something that was spent in the past, or double spend something between them, like this transaction and this transaction is trying to spend the same coin. Okay? Now, I have these transactions. Actually, I'm trying to simplify it. I add also one more transaction, which we call the reward transaction. That's the money that you will get if you find the solution. Okay, and that's how a block looks like. We have the transaction, and we have what we call a header, the header of the block. So quickly, the version is the version of the protocol that we are running. The previous block hash, so it's a hash of the previous block. Okay, and then think about this as a compressed version of all the transactions. So this record represents all the transactions. So if you change anything in the transaction, this has to be changed. Okay? And then some timestamp to say I mined this at that time. And then some field that indicates the difficulty of the problem, how difficult the problem that we are trying to solve. And the nonce. What is the nonce? This is what we are searching for. Okay. This could be a bit hard. So we are trying to hash this header and find the nonce. So as we said, when you use SHA-256, every time you change the input, the output will change, right? Right. So we are trying to search for the nonce such that when you hash the whole header, the result will be less than some number. Okay? We'll call it the difficulty number.
So are you going to define that word, or is this a word that everybody knows exactly?
Which word?
N-O-N-C-E.
Oh, the nonce. Think about it as a number that just a number that a random number that we are generating.
Is that the solving of the puzzle?
So to solve the puzzle, you need to find some number that you concatenate or you add to the header, such that the hash of the whole header is less than some number. Okay? So the mining is to find this nonce or this number that achieves this inequality. Yes?
Is that number unique?
No.
Okay.
No, it's not unique.
Okay.
So let me, I would like to use the board, but I don't know how many of you will be able to see what I'm going to write. So let's say the output of SHA-256, let me use a better marker. The output of SHA-256, let's call it SHA-1000, okay? You give it a string, X, and it generates a number from 0 to 999. Okay? Now, if I tell you what is the value of the nonce, that if you concatenate on X, the number that's generated by this function is less than 999. How hard is this? So any nonce can work, right?
Yeah.
Any nonce. Any number you concatenate here, we guarantee because the output is either from 0 to 999. So any number you add to X will achieve this inequality. Or equal. Okay? Now if I take one of these digits and put 0, now does any number in the nonce will achieve this inequality? No. 10%.
Is it linear like that?
So it's actually not linear, it's exponential. So think about it. I mean, 10% of the nonces will generate number from 0 to 99, and the rest of the nonce will generate numbers from 100 to 999. Correct? Yeah?
So the 256 in SHA, that's 2 to that power is the number of possible.
As a number of possible solutions.
Okay.
Right? Okay, now let's take another 9 and make this 0. So now, how many nonces will generate a valid answer here?
1%.
1%. Okay? So every time I add a 0 here, the problem becomes much harder. Now in SHA-256, instead of using decimal system, we use binary systems. Instead of saying converting 9 to a 0, it's converting 1 to a 0, but it's the same idea. We are looking for the nonce that generates a number less than the difficulty. Yeah?
So what's D?
What's D? That's a good question. So D, of course, has to be 256 string of bits, right?
It could be all zeros and a 1.
Right, so now D determines how many, so, I mean, okay, let me jump a little bit and then I'll get back. So for D, so this is what we call dynamically adjusted difficulty, okay? So think about it as 256 bits, like the 999, the 999 that we used in this example. Now, every time I add a 0, or say that the difficulty bits are 10 or 20, every time you increase the number of difficulty bits, the problem exponentially gets harder. Okay? So that's an example. I mean, if you understand this slide, I would be super happy of this talk. This is the most important slide in this talk. Anything else is just whatever. Yeah.
Oh, and so this also means that there is a hard limit to how difficult this problem can get.
Right. So we're going to talk about this in a couple of slides. It's like we want basically to generate a block every 10 minutes, right? So this it depends on how many nodes are in the network, because all these nodes are searching for a solution. So if the nodes increases, what we're going to do is to increase the difficulty bits to ensure that at most 1 block every 10 minutes, or around 1 block every 10 minutes. If the miners are saying, oh, it's not worth it, I'm going to turn off my machines, now the difficulty has to be adjusted to the number of miners in the system. Okay? Yes?
Is this to make it like just kind of random who gets the solution?
Yes.
Okay.
So who gets the solution? The one that has more computational power to try many, many nonces to achieve this inequality. Yes?
So who is setting D?
Yeah, so that's, if we end up saying that someone is setting D, then it's centralized, right?
Yes, yes.
So we need a distributed algorithm that we all agree on to set D. That's a very good question. Next slide. Promise. Okay, so let's go back a little bit, just talk about the TX, the transaction reward. Remember when you asked me about the first signature? That's the one. This transaction is self-signed. I signed it to myself to give myself that many bitcoins because I mined this block. Okay? So it's self-signed. I signed it to myself. But why everyone would accept it? Because this transaction resulted in generating this block. So we mined the block. So people have to make progress, so they accept my solution. And they accept that I now own this 12.5 bitcoins, which is the current reward, and we'll move forward. Yes?
So the very first block has only one transaction.
So you could actually have blocks that has no transactions, but has the reward transaction only.
Okay.
Yeah. So it doesn't have to be only the very first one. It could be any block,
Okay.
as long as it's consistent.
Yeah.
Yes?
What prevents the person who's self-signing the reward to make it like 1,000 bitcoins?
If you do that, no one will accept your block. You will announce to everyone saying, hey, this is my block, it's consistent. Everyone can verify that this block is consistent. How would they verify? They verify that this header, when you hash it with this nonce, it's less than D, right? Notice that the transactions in this block are compressed here. And one of the transactions moves money to yourself, right? So what makes this block unique to you is that basically the compressed version of the transaction has one transaction that moves money to you. If you move more money than 12.5, this block will be rejected. Okay?
But that number also changes, right? You're saying
It changes every to 210,000 blocks.
Oh, okay. And so that's agreed in the descent, like with the descent.
So that's a parameter in the algorithm. So basically, if we have block 0, now in block 210, we're going to change half the reward. Okay? Yes?
So, yeah, I have two questions. You asked one. And the other one is, does
Whoever finds a block solution.
It is like it's worth the same. Like
Yes, it's worth the same, and the reward keeps, it's halved every that number of blocks.
Okay. Just
Okay.
goes up. It's never gonna go down.
It goes down, it's halved.
Oh yeah.
Yeah,
But it's never gonna go up.
it's never go, I mean, unless someone wants another version of the blockchain. For this blockchain, no, it's not.
Okay.
Yeah,
If I find a solution,
correct.
is there something to stop me from holding on to the solution until like D drops? Like say I assume that people will drop out of the network for some reason.
Okay, so there are many points on your question. One, why wouldn't you hold on to your solution? You could, but you will be afraid that someone else will find another solution, and if someone else finds another, notice that this is a set, right? As we said, the nonce is not a unique nonce. It could be many nonce, right? So someone else could find another solution and publish it to everyone. Now who wins? The one that tries to reach more people first, okay? So yes, you can hold your solution, but you risk that you can lose the reward, okay?
So what if two separate people?
Very good question, next. Let's carry on.
Can I ask a question first then?
Sure,
So in our current monetary system,
yes,
money is actually created from nothing.
right,
There is no energy expended like there is in this.
Right, right.
It's just the whim of those who are, by law,
Right.
kind of the top people. This system is actually creating money out of
effort,
energy expended.
right.
So this is a much fairer system.
This is a system that would say there is enough effort that was spent to create this money. So it wouldn't inflate forever. So that's why there is a hard limit on the number of bitcoins that could exist at any moment. So yes, it's again, I mean, I assume it's similar to the gold mining idea. So we give gold some value because we spent a lot of effort in mining the gold, and it's scarce resource, it's not found everywhere, so it's pretty much similar, but it's a digital version of it. So that's how I see it, yes?
Would there be anything, I mean, it would be kind of silly to do this, but there would be anything to prevent someone from giving themselves less of the reward than they should get? Like maybe people come to the agreement, it's like, oh, we should cut Bitcoin off early, like.
I mean, the number, the reward is set in the protocol. And all the nodes who are running the protocol agree that this is a number that should be as a reward. Any block that has a different reward value is not a valid block from this protocol perspective. Maybe it's a valid block from another protocol perspective, but from this protocol, where all the nodes are running the same protocol, they wouldn't accept it.
So, but like from the perspective from the rest of the network, they wouldn't care that, like they would see, oh, this guy gave himself less reward than they should get, might as well just add it on, maybe?
That wouldn't happen. I guess that wouldn't happen. Okay. Yes.
It might not be fair because then you have, besides the nonce area, you have another area where you can play around with numbers to find the header that's like a little bit fit. So it still wouldn't be fair. Because let's say it's 12.5, you try 12.09, 12.899, and so on, together with the nonce. So you have two areas. Does that make sense?
Not really, because the problem is really hard for any number.
Yeah.
Like searching for the number is like searching for the nonce. So, yes.
Because I know like they use this time, because they have some wiggle room in terms of timestamp, right?
Yes.
So they use the timestamp tool as another additional area to play around with numbers.
But anyway, the problem itself of finding the nonce with this combination is super hard on its own for any combination of these fields. So finding the nonce for one or the other, it's as hard. So you don't have any incentive to try for many of them. You know what I mean?
Oh, I have one more. For the field current target bits,
Right.
what does that correspond to?
So the current target bits is basically the number of difficulty bits.
Oh, okay.
How many? 20, 25, 23? Yeah? So that's basically the number of difficulty. It's adjusted every 2016 blocks. Okay, so difficulty. Someone asked me how would we set these bits, right? And it has to be a distributed algorithm. It cannot be a centralized authority or organization that says what is the difficulty. So basically, we want to adjust the difficulty every 2 weeks or 2016 blocks. It's basically multiply 10 minutes by 2016 to give you the number of minutes in 2 weeks. Okay? So now if we are at block 0 and we mine 2016 in 1 week, what does it mean?
It's too easy.
It's too easy, right? It means that we have double the computational power because we generated as many blocks, double the number of blocks that we should have done, right? So by doing that, what we can do is to say, okay, take the current difficulty and multiply it by 2. So the actual time, you can calculate the actual time that was taken to compute 2016 blocks. It's basically the timestamp of the block 2016 minus timestamp of block 1. And then say that the new difficulty equals the old difficulty multiplied by the expected over the actual. So basically, if the actual time is much less than the expected, 1 week, and this was 2 weeks, the new difficulty will be 2 times the old difficulty. And by doing that, it can be done in a distributed way. We can all, if we all run the same algorithm, we'll end up having the same difficulty. Does that make sense? Of course, if the actual time was much more than the expected, what's going to happen is that the new difficulty will be less than the old one. Okay, so it's self-adjusting. And that's also part of the beauty of the protocol. So, sorry, I don't have a pointer, so. Anyway, so, yeah. So the big picture is that everyone has a copy of the blockchain. Once one find a block or mine a block, they send it to everyone. Now the question is, why would we accept this block and move forward? So, because it's super hard to solve this problem, and the probability for us to find a block is super low. So it's the probability of us to find, so in this case, we are looking for the force. Someone said, I found the force. The probability of us to find the fifth after appending the force is as equal as for us to find another fourth block. So we might as well accept the current fourth block that was announced by someone else and look for the fifth. Because probability speaking, it's almost equal. Yes?
What happens if two people on opposite ends of the block find the next one in close time proximatity,
Right.
enough time for some transactions
Right.
to happen before everyone can check?
I promise that this will come next.
Okay.
Before. So, yes. So, we have to send to everyone. They accept it. Why they accept it? Because the probability of me to find the same block is equal to find the next one. So I might as well just accept this and move on. So, find the nonce that result in the SHA-256 of block less than difficulty. The solution is a set. Once solution is found, a block is mined. It's easy to verify. So some properties of the mine block, it cannot be pre-computed. Why? Because it depends on the current block transactions and the previous block hash, right? As you remember, I cannot pre-compute block 20 if we are now at block 15. I can only start mining block 20 if I know 19, because I depend on the hash of the previous block, right? And as we said, if you change anything in the original string, the SHA-256 will be completely different. Okay, it cannot be stolen. So how would I prevent someone else from taking my mine block and say they mined it? Basically, the reward transaction is moving money to myself. So if someone else say, hey, this is my block, it's fine, it's your block, I don't care, because it's moving money to myself, to my public identity. So whoever mined it, it doesn't matter. It cannot be stolen. And then network node accept the first block. Why? Because the problem is super difficult and there's no guarantee bound to find another block. So I might as well just accept this block and move on to do the second. So that's your question, was what happens when two nodes concurrently mine a block? We call this situation a fork, and forks are bad, are really, really bad. So you have two miners, one mined the green block, the other one mined the red block. As we said, the miners validate transactions. You have to make sure that these transactions are not conflicting with the past, and they are not conflicting with each other. So this miner did that for the green block, and this miner did that for the red block, right? But no one did the conflict check between this block and that block. Why? Because they were generated at the same time. So I'm always comparing with the history and the current transaction in the block, right? So no one compared these to each other. So this situation could lead to double spending. How? Bob tries to double spend the same coin twice in two transactions. One in this block and one in that block. Okay? So this must be prevented. So how would we prevent that? So here is what happens. Fork has to be eliminated, they are bad. So what's going to happen is, I found this block, so I send to part of the network saying, hey, I found this block. So they will add it to their blockchain, they will verify it's correct, and they keep searching for the next one. This guy will do the same. Send their block to some group of the miners, and try to convince them that this is the block, and it's actually a valid block. So it will be added to some mining nodes, and they'll keep searching on this path. What's going to happen is that once any of them, so think about it that the network is now split. One is searching in the green, and another one is searching in the red. What's going to happen now? Maybe the green will find the next block first. Or the red will find the next block first. But one of them most probably will find the block, like the fifth block before the other one. Okay? If this happens, what's going to happen is that all the miners now can see that there is a chain that is longer than the chain that they have. So they join this chain and mine for the next blocks. Why? Because think about it. If I'm mining here, which block am I mining for? The fifth, right? And I'm promising myself that I'm getting the reward of the fifth block. But someone already found it. And people are going to mine on the sixth now. So they wouldn't accept mine. So I don't have incentive to mine on the fifth here anymore. My incentive is to join the longest chain. Okay? Because even if I found the fifth block, maybe by that time these people will find the block number 6, so I will lose my reward. Okay? Yes?
So the owner of the red block get punished.
So the owner of the red block, in some sense, yes, they lose the rewards. Right. Right. It's not, I mean, I don't know if it's fair or not, but it's to prevent something that bad that could happen. Okay? Yes?
Okay, so it's not about the transactions, it's about the word fork.
Right.
In cryptocurrency, isn't there another way that the term fork is used? Like when they did Bitcoin and Bitcoin Cash, I think it was. And
Hard fork?
don't
So-
they call that a fork?
So, yes, that's another story of forks. But, okay, the forks that we're talking about is basically miners that are running the same protocol. Okay? There are 2 other types of forks, which is basically saying, I'm going to do a hard fork or a soft fork. Soft fork is basically, I'm going to take your protocol and create a new coin using the same protocol or another variation of it, like Litecoin compared to Bitcoin. They are more or less using the same protocol but for different coins, right? And then there is Bitcoin and Bitcoin Cash. It's called hard fork. It's basically saying, I'm going to copy the history of this chain and take it, and anything that starts from here is going to start with a new protocol. Like we're going to change the block size or change the consensus protocol or something. This is what we call hard fork. But what we're talking about here is fork in the same protocol in the same network. It's not a new coin. It's a bad thing that shouldn't happen in the same network. Okay?
Question.
Yes.
So when the owner of the red block gets punished,
Right.
what happens to the transaction that has already benefited?
Very good question. So basically the transactions here, there was some promise that they are committed, right? In some sense. They are added to the chain, but they are going now to be abandoned. So what's going to happen is that they have to be resubmitted. So basically if there was a transaction that was spending the TX2 and TX1 here were conflicting, now if you abandon this and try to resubmit it, TX1 will be compared to TX2 here, and any double spending will be detected. Yeah? So they have to be resubmitted. So what's going to happen here is that the miner joins the longest chain to resolve forks, and the transaction, this block, have to be resubmitted. Yes,
So that means that anyone wanting to do a transaction, any sort of transaction,
right.
has to do that transaction when one of these blocks, when the next block is found. Like I can't send money to my friend whenever I feel like it. I have to send money when someone finds the next block.
So you, so many points in your question. I will try to address them all. You can send money whenever you feel like it, but the confirmation that this money is sent, you have to wait until your transaction is in a mined block, and it's not only that, it's deep enough in the network. Why? Because as soon that your block is here, your transaction is here, a fork could happen, and all these transactions could be abandoned. So in blockchain, there is this magic number. They say 6 blocks. After 6 blocks, you can assume that your transaction is committed, which means an hour.
Okay.
So for a committed transaction, right? But I mean, one would think about, oh, an hour is a lot for a Visa transaction and swipe of a credit card, right? But an hour is very little if you want to send money cross countries,
Sure.
right? And if you want to send $1 billion, I mean, conceptually. Anyway, yes.
So you said the depth to be 6, but
That's a heuristic. I mean, don't quote me on that. I mean, it could be. I mean, I would say you should change the depths depending on the amount of money that you're spending or you're transferring. So I would say if I'm transferring $10, maybe after 1 block, it's fine. Right? I don't care. No one has an incentive to revert this block because of a $10. Right? But if I'm transferring $1 billion, then one could do the math, how much a block mining costs, and then divide $1 billion over that and see how many blocks you should wait, approximately. But there are some statistical analysis in the Bitcoin paper. You can go and read it. Yeah. Other questions? Good?
Me about you answered.
Okay. Yes.
Just a general question. So
Uh-huh.
if you're mining and you try to cheat in some way, like you give yourself more than the agreed upon reward,
Right?
then and then you send the block out,
Right?
everyone else is going to reject it,
Right.
right? But if you control enough of the network,
Correct?
then you can give yourself whatever reward
You can
you
do
want.
whatever you want if you control enough of the network. So that moves to the next slide, which is the 51% attack. We're always one slide ahead, guys. Okay, if 51% of the computation or hash power are malicious, they're trying to do something bad, they can cooperate to fork the chain at any block. As we said, the rule is that everyone is going to join the longest chain, right? Because the longest chain proves that it has the most computational power. And usually it's the assumption that the good people are more than the bad people. I mean, and this assumption, some people in computer science proves this by saying, okay, because we have society that proves that good people must be better than, outnumber the bad, because we have society. And that's the proof. But anyway, so if 51% of the computational power is owned by malicious people, it can lead to double spending. How is that? I could spend my coins in the green block, and then go on the other side, because I have 51% of the computational power, then I have higher probability to find blocks than everyone else in the network. Maybe the other people found another block, and people consider this transaction committed. What I'm going to do is fork here and generate a longer blockchain. So everyone will join this chain and abandon this one, and hence this transaction will be abandoned. So if I convince someone that they took my coins and give me their car, then they took the car for free, in some sense. Okay? That's 51% attack. Question now is, how much does it cost to do a 51% attack on a Bitcoin network? There are some research, you can go read some papers. Recently, I read an article that it's around $350,000 per hour. So it's a lot of money per hour. So per hour, yes.
But not that's human amounts, that's the amount of money that banks do actually spend on things.
Sure. I mean, But how much forking do you want to do? I mean, do you want to fork from the last block? Anyway, no one trusts the last block. You always want to fork like from way in the past because people back by then will consider that these transactions are committed. So, yeah, and the more the computational power in the network, the more it has value, and the more it's hard to fork it. Okay, I think I'm gonna stop here. Take more questions. Anyway, with that, I would say very few words about the limitation. There are high transaction confirmation latency if you're talking about like credit card type of transactions. There are probabilistic consistency guarantees. Like when would you say the transaction is committed? It's probabilistic. Could be forked at any moment, but the probability of fork goes down exponentially. It's very little transactions per second, from 3 to 7 transactions per second. If these transactions are transfers cross country, then it's fine. But if they are just swipes of a card, then that's very little. Yes?
That's by design,
That's by design. And yes, that's by design because the block size is very small. And each transaction takes
10 minutes.
Yeah, we want a block every 10 minutes. Right? Yes?
Does this mean like within the United States, every second there might be 1,000 people swiping the Visa card, but if they all switch to Bitcoin, every second only 7 people can do this?
So far, yes. There are many efforts on how to scale this that are happening now. I guess you can think of the Bitcoin network as a medium of transfer, something like gold. You don't often transfer gold. You don't often transfer cross-country funds, right? But if you want something like Visa transactions, there are solutions that we call them off-chain. So we do transactions off-chain between peers, but then we think with chain. I mean, yes?
What is the problem of expanding the block size?
I'm going to talk about that in a second. That's my last slide. I took a lot of your time. So how to scale Bitcoin? There are 2 obvious solutions. One is increase the block size, and the other one is decrease the block interval, right? So each of these has very obvious problems. I'm going to mention a little bit, and then I'm going to stop here and take any last questions. So why don't they work? I mean, many hard forks try to increase the block size, but I mean, the problem is when you increase the block size, say, instead of saying 1 megabyte, I'm going to make it 64 megabytes, or 1 gigabyte, right? So the problem with that is that it requires the miners to have storage capabilities and network capabilities that that not everyone could handle. Okay? So it's kind of decreased fairness, giving like large miners advantage. Okay? But the other thing is that, I mean, to transfer 1 gigabyte to the whole world versus transfer 1 megabyte, the latency could play a lot of problems there. So it requires more storage and verification time. Now, if we decrease the block interval, saying that we are going to generate a block every 5 minutes, the problem with that is that it leads to a higher number of forks, because the only way you can decrease the block interval is by reducing the difficulty, which means the probability to find the solution gets higher, which means the probability of forks increases, right? So these 2 solutions are always like the easygoing solutions, but they're not actually what people are looking for right now. Anyway, the rest of this slides talks about some alternatives in academia and stuff. There are also a few slides at the end about Lightning Network, which talks about off-chain transactions, atomic swap. These are like the topics that people talk about. You can find a full copy of this on my website. Basically UCSB Victor Zakhary. So it's cs.ucsb.edu. And then there you will find a copy of the tutorial, this tutorial slides. And that's it.
Would you give that again for the slow ones amongst us?
You mean the presentation?
No.
Oh.
Yeah, right, start all over.
But I mean the slides?
Your website.
Yeah, it's here. It's basically cs.ucsb.edu/Victor Zakhary. And there you will find a link to, I'm not sure exactly about the link. I mean, but you'll find it on this page.
Or if I'm on the website right now, do I have to go to graduate and then find you and then click on it? Or how does it
No. Yeah, that works. It's listed as the PhD student.
Wait, can you set up?
So that's the website. Anyway, I'm not doing advertisement to myself, but the slides are here. It will take some time, but yeah. Okay?
Thank you.
Thank you.